In semiconductors, for electrons to become free, they must be promoted across the energy gap or energy band gap into the empty states at the bottom of the conduction band. Only the free electron will participate in the conduction process, and for that purpose the electron must be promoted from valence band into the conduction band. Now, in intrinsic semiconductors, the valence band is completely filled and the conduction band is empty. The conduction band is empty at absolute zero. This is the valence band. This is the conduction band. The valence band is completely filled, but conduction band is empty. Now, by supplying an energy which is approximately equal to the band gap energy, the electrons from the valence band can be promoted into the empty states in the conduction band. Now, what happens when you move an electron from the valence band to conduction band? Moving an electron from valence band to conduction band leaves a hole in the valence band, which is shown in the figure. When the electron is promoted across the band gap into the conduction band, it leaves a hole in the valence band. Now, this electron in the conduction band will become the free electron. When you apply an electric field, what happens? The hole may be seen as moving. When you apply an electric field, the hole may be seen as moving because other valence electron in the valence band will fill the hole. Thus, in the presence of electric field, the electron and hole will move in opposite direction. The electron and hole moves in opposite directions. This is represented using an example of silicon. When the electric field is applied, the free electron and hole are moving in the opposite direction. Intrinsic semiconductors have poor conductivity. It is because a very small fraction of valence electrons are excited into the conduction band. A very small fraction of valence electrons gain enough energy to reach the conduction band. That means a small number of electrons are there in the conduction band. These few electrons in the conduction band are responsible for the poor conductivity because the current flow is limited when you apply. Now let us discuss about N-type extrinsic semiconductors. Consider silicon, which is an intrinsic semiconductor. Silicon has 4 valence electrons. Silicon has 4 valence electrons. Now, each of which is covalently bonded with adjacent silicon atoms. Silicon has 4 valence electrons, each of which is covalently bonded with adjacent silicon atoms, like this one. Suppose you consider an impurity atom with valence 5 is added as a substitutional impurity. It may be phosphorus, arsenic or antimony. Then what happens? Now the 4O5 valence electron in the impurity atom will participate in bonding, in covalent bonding. When 4O5 valence electron is participating in the bonding means there is one extra non-bonding electrons. There is one extra non-bonding electron which is actually loosely bounded with the impurity atom. Like this one. That is, we have a donor state which contains electron and from where the electron can be excited into the conduction band. Now, whenever there is an excitation, each excitation event supplies a single electron from the donor state into the conduction band. Therefore, these kind of impurity atoms are called donor impurity because it can donate electron to the conduction band. Now consider the excitation events. When each donor electrons are excited from the impurity levels into the conduction band, please remember that there is no hole is created in the valence band. Here the excitation is not happening from valence band, therefore no hole is created in the valence band. Now the donor state is very closer to the conduction band, therefore at a room temperature a small thermal energy is sufficient to excite large number of electrons from the donor state into the conduction band. Now what is the consequence? The number of electrons in the conduction band is exceeding the number of holes in the valence band. Please remember that during the process no hole is created in the valence band. These type of semiconductors are called N-type extrinsic semiconductors. Here the majority carriers are electrons and minority carriers are holes. Now let us discuss about p-type extrinsic semiconductor. Once again consider silicon which has 4 valence electron. Suppose trivalent impurities like aluminum, boron or gallium which are added as substitutional impurity into silicon. This is represented in the figure. Here we have used boron as the impurity. Now we can clearly see that one of the covalent bond around each impurity atom is deficient in an electron. This electron deficiency we will call it as hole. Such deficiency or hole which is weakly bounded to the impurity atom. So we have a hole which is weakly bounded to the impurity atom. Here it is boron. Now, in order to participate this hole in the conduction process, this hole must be liberated from the impurity atom. The hole is liberated from the impurity atom by the transfer of electron from adjacent bond. By the transfer of electron from adjacent bond, now the hole is free, and when you apply an electric field, this hole will move and participate in the conduction process. This moving hole participate in the conduction process. So what actually happens? The electron from the valence band is excited into the acceptor state and a hole is created in the valence band. Now the impurity of this type is called acceptor impurity because it can accept electron from the adjacent bonds. It is capable of accepting electron from adjacent bonds in the valence band. Now, the energy level introduced by this type of impurity is called acceptor state, which is represented in the figure. This acceptor state is closer to the valence band. When the electric field is applied, this moving hole will participate in the conduction process. Now, in a p-type semiconductor, the majority charge carriers are holes and minority charge carriers are electrons. The next topic is Hall effect. What is Hall effect? If a magnetic field is applied perpendicular to a current carrying material, then electric field is produced, the electric field is generated perpendicular to both the current and the magnetic field. Here B is the magnetic field and I is the current which is passing through the material. Both are perpendicular. Then Hall effect says that there is an electric field is generated which is perpendicular to the current and magnetic field. Now a Hall voltage is generated. The value of the Hall voltage VH is equal to RH by D into IB, where I is the current, B is the magnetic field and D is the thickness of the sample. Here RH is the Hall coefficient. Now for electrons, this Hall coefficient is minus 1 by Ne, and for holes, the value of the Hall coefficient is 1 by Pe, where N and P are the concentration of electrons and holes respectively. The Hall effect is used to determine the type of semiconductors we have. How it is possible? Just to measure the Hall voltage VH using a voltmeter. Now, if we know the current, the magnetic field and the thickness of the sample, here D is the thickness of the sample, then using equation 1, you can find out the Hall coefficient RH. You can find out the Hall coefficient RH. From the sign of RH, you can determine the type of semiconductors you have. If RH is positive, that means the material is p-type, and the obtained RH is negative means the material is n-type. Also, using equation 2 and 3, you can find out the concentration of electrons or holes in the semiconducting material.